Welcome back. In this video, we'll be discussing how the X-rays are detected in order for a final image to be produced. The two most commonly used methods of detection are semiconductor detectors and X-ray films. We'll start with semiconductor detectors, which are a form of digital radiography. Semiconductors are materials which have resistance between that of conductors and insulators. They are mostly made from silicon and germanium, with some impurities added. Their behaviour is governed by the energy band gap, Eg, which is often a few electron volts in magnitude. This is the energy barrier an electron must cross in order to move from the valence band to the conduction band. Electrons in the conduction band have sufficient energy to move freely in the material and allow a flow of electric current. Those in the valence band do not. Initially, electrons will lie in the valence band, and the Fermi-Dirac distribution will describe the probability of an electron being at a certain energy, E. In this equation, EF is the Fermi energy, T is the absolute temperature, and K is the Boltzmann constant. When an X-ray hits an electron in the valence band, the electron absorbs its energy and may have enough to jump the band gap and exist in the conduction band. Note that in order to ensure no electrons already exist in the conduction band, it is sometimes necessary to cool the semiconductor. The decrease in temperature reduces the probability of electrons existing in higher energy states. This is confirmed by the Fermi-Dirac distribution given above. We will now discuss this process in more detail. Electrons are transferred from europium-2+ in the valence band to fluoride+ in the conducting band. This leaves europium-3+ in the valence band and a stable fluorine atom in the conduction band. Europium-2+ has lost an electron, while fluoride+ has gained one. In order to process the image, energy is provided to electrons in the conduction band. This is in the form of red light photons at 700 nanometers. The original process is reversed as fluorine atoms lose an electron to form fluoride+ ions, and europium-3+ ions gain an electron to form europium-2+ ions. Energy is released when the electron drops back down to the valence band. This energy is in the form of photons in the blue visible light spectrum, from 400 to 450 nanometers. The red laser light is reflected by a rotating mirror and is shone along an axis of the X-ray cassette. The blue light, which is produced, travels through optic fibers to be converted to a digital signal. Any red light which is captured by the optic fibers will be filtered at the base of them. Optic fibers are a mechanism of transporting light radiation. They are composed of two materials of different optical densities. These are the core and the cladding. The core must have a significantly higher refractive index than the cladding to ensure total internal reflection of the light throughout the core. The condition for total internal reflection is of course given by Snell's law, such that the angle of incidence is greater than the critical angle. The sign of this critical angle is the ratio of the refractive indices of the cladding and the core. The blue light is sent through the optic fibers to a photomultiplier tube. Here, in step 1, the incident light strikes a photoelectric surface. Photoelectrons are emitted. However, there are too few of them to measure a significant electric current. The photomultiplier's job is to increase the number of electrons by a known proportion to allow a current to be measured. To do this, the photoelectrons are focused through a focusing electrode, step 2. This accelerates the photoelectrons and directs them towards the first dynode. The acceleration occurs due to there being a high potential difference, usually 90 to 100 volts, in the vacuum between the focusing electrode and the first dynode. Electrical potential energy is converted to kinetic energy and the electrons speed up. The dynode is a photoelectric material where the focused accelerated electrons provide an energy equal to or greater than the binding energy of the electrons within the first dynode. This causes a secondary emission of electrons from the first dynode, step 3. Each dynode is held at a higher potential difference to the next, causing further emissions of electrons from each, step 4. Once the electrons have passed every dynode, a measurable current is detected at the anode as the number of electrons has increased significantly, step 5. This current is a function of the number of blue light photons which initially hit the primary photoelectric surface, and is therefore a function of the number of X-rays which initially hit the cassette. The current obtained for an element of the cassette is sent to an analog to digital converter. The X-ray can then be presented digitally. A smaller digital signal will correspond to fewer X-rays and therefore a structure with a higher mass attenuation coefficient, such as bone. A larger digital signal will correspond to more X-rays and therefore a structure with a lower mass attenuation coefficient, such as tissue. Now let's discuss film radiography, starting with the setup of the X-ray cassette. The radiographic film is sandwiched between layers of foam and an intensifying screen. The layers of foam ensure a compression of the intensifying screen against the film. It is crucial that there is no space between these two components. The intensifying screen converts high-energy X-ray photons into lower-energy optical ones. This effect is called luminescence. X-rays are absorbed by electrons in the molecules of the intensifying screen. Once the absorption occurs, the electrons are promoted from their ground state to an excited state and remain here for a short lifetime, usually 1 to 10 nanoseconds. During this time, some of the electron's energy is lost in a process called vibrational relaxation. Here, a proportion of the electron's energy is released to its surrounding lattice. When the electrons leave the excited state, they release the remaining energy they took up in excitation. The energy is emitted as an optical photon with a longer wavelength than the initial photon. This increase in wavelength is called the Stokes shift. The next layer is the radiographic film. It is composed of two parts, the emulsion and the plastic. The emulsion layer is a silver halide lattice disrupted by some sulfide ions suspended in gelatin. The optical photons released from the intensifying screen initiate a chemical reaction in this layer, which results in a silver atom being deposited on the plastic. The areas of the plastic where the silver is deposited produce the dark parts of the image. We would like to end this section on X-rays with a note of safety. X-rays are high-energy photons. The photoelectric effect they induce in tissue is potentially harmful if the exposure is too high. The radiation's high ionizing power can cause instabilities in the molecular structure of the cell. In particular, the cell's DNA can become damaged and the double helix structure can split. The X-ray machines are shielded by lead. Lead has an extremely high mass attenuation coefficient of about 7 centimeters squared per gram, so a very high proportion of photons which hit the lead are absorbed. As well as the machine being shielded, protective clothing such as lead aprons are worn by the person operating the X-ray. Thanks for watching this mini-series on X-rays. The next video will focus on another imaging technique called ultrasound.